Assalamualaikum dan salam sejahtera semua. So kita akan sambung sikit lagi on our last topic, how to construct AC voltmeter using what we call a full wave rectifier. Okay, before this kita discuss about half rectifier. So kita akan now continue macam mana kita nak construct an AC voltmeter using a full wave rectifier, which is also called also known as bridge rectifier. Okay, so it's like this. If a full wave rectifier circuit, this is a full wave, let's say this is a block diagram for a full wave rectifier, is connected before to the DC voltmeter, then the entire combination together is called AC voltmeter using full wave rectifier. So this is the block diagram. So we have an AC input, and then you're going to feed that AC input into a full wave rectifier circuit and connect to the DC voltmeter, and then the DC voltmeter will also output a DC reading. Okay. So there are two blocks as usual, the full rectifier circuit and also the DC voltmeter circuit. We will see that in a moment. And okay, let's go next. Okay, let's go straight to the point. So now you are given the same, we will also try to measure the same AC voltage, different magnitude of VM. This is the input voltage, and it's a periodic sine wave. Okay, and to construct a full wave bridge rectifier, you need basically at least 4 diodes, and they are arranged in such this way of arrangement. Okay, so if you flip the direction of diode the other way around, then it will be different. Okay, so it has to be 1, 2, 3, and 4 diodes arranged in this way. Okay. So in this way, it will enable signal to pass through at all cycles. What do you mean by that? Okay, so let's say, for example, during the first half cycle, this one here, and let's say for the first positive half cycle, the current will flow through this way. Okay, so according to the diode function, so the diode will allowing one direction of current flow, right? So it will flow to this junction, and it will flow through D2, right here, because it will not flow through D1. D1 is basically doesn't allow the current to flow that way. So it flow D2, and then it will also not flow through D4 because this arrangement will also block the current flow downwards. So it will flow to here through the resistor and through the meter, okay, and go through this path, go up, and then cross over, and then it will go to D3. It will not go to D4, D3 again. Okay, this here, and then it will go back into the negative terminal. Okay, so what happens is that for the first half cycle, all the current will pass through. So basically, the output, the voltmeter will see the entire full voltage of the input. So the same voltage, this is VM. So this is VP. This could also is equal to VM. Okay. All right. So okay, now let's take a look what happened to the negative half cycle. Okay. So when the input voltage is in the negative half cycle, so the current will flow from the other side, okay, from this way. All right. So when the current flow this way, and then it will come to the junction, and it will not flow to D3. Okay, it will go through D4 because that is the direction that the diode allow go flow this way, and then it will not flow to D2 because the current cannot go this way. Okay, so it will go to RSE, the series resistor, and through the meter. Okay, and then we go all the way down and all up, and then we'll cross this, and then it will go up, and then of course it will not go through here. Okay, it will go to D1, and then the diagonal cross, and then it will not go down here. It will go straight back to the positive terminal. So you can see at both situations, the current IM will always flow either positive cycle or negative cycle. So during positive cycle, you will have this full voltage pass through, and the negative cycle will also see the same voltage, except now it is reversed. Okay, because it's positive, because the current flowing in the meter is in the same direction, it's not the opposite direction. Okay, so to the average value for the full wave rectifier is basically twice the 0.318 multiplied by the peak voltage, which is 0.636 multiplied by the peak voltage. Okay, so this is to show you a simple animation on how the electron flow during the both positive cycle and the negative cycle. As you can see, in any situation, either positive or negative, the current will always flow at the same direction. No, in this arrow, basically showing the electron, the flow of electron. But you can see the flow of current is this way. Okay, it will always flow in the same direction, no matter the input is giving positive cycle or negative cycle. So basically, just to summarize that, if you have like a single diode, okay, maybe there's a resistor here, doesn't matter. So if you have an input voltage, a full sinusoidal voltage, and your output voltage will only give you half of the voltage. Okay. If you put a rectifier circuit, this is a full wave rectifier circuit. Okay. The half rectifier circuit is this one. The full wave is this one. Okay. So if you have the same input voltage as this one, and then if you connect it to the full wave rectifier, then your output voltage will reveal a shape like this. So you will have more positive voltage compared to this one. So you can see that the output has more average value than the half wave. Okay. So this is how it looks like in a circuit. How to connect the AC source, and then this is the bridge rectifier circuit to the PFMC instrument. Okay. So so basically, comparing both half rectifier and full rectifier, you can see that it is more desirable to use. It's more desirable. It's much better to use a full wave rectifier rather than a half rectifier because of higher sensitivity rating. Okay, because as you can see, the full rectifier allow more voltage to pass through the to the meter. So basically, the most frequently used full rectification is called a bridge type rectifier. That we have just seen just now. It's just called a bridge type. There are actually many types, but this is the most frequently used. Okay, so let's continue. So this is just a picture just showing you that remember the circuit diagram that I showed just before, how the current flow for each of the positive cycle and negative cycle. So as you can see, the current will flow at both cycle, the current still flow through these 2 meters. So that's the advantage of this full wave rectifier circuit. Okay, so this is also just to explain again. Okay, during the one that I just explained just now. So D2 and D3 will conduct in positive high cycle, while D1 and D4 will conduct in a negative high cycle. So same thing I just explained before. But you say that D1 and D3 cannot be on at the same time, and D1 and D4 cannot be conduct similarly at the same time. So basically, it is just a crisscross kind of combination. So the maximum voltage across the load for positive, okay, let me move the video here. Okay. Okay. So the maximum voltage across the load for positive and negative cycle is Vp. Okay. And we know that the average output voltage for each period is, okay, so the average voltage is 1 over the whole period multiplied by the integral between 0 and t, the whole voltage dt. Okay. So if you split that into two, whether into positive and negative cycle, so you will have the integration, the voltage not, okay, for positive high cycle and negative high cycle. This is just for the revision purposes only. So since current flow through the meter movement at both half cycles, we can expect the deflection of the point to be greater than with half rectifier. Okay, all right. So it makes sense because for full rectifier, more current at all time will flow through the MMC meter. So for positive high cycle, if you integrate the peak voltage sine dt, you will have basically 2 times peak voltage. And for negative high cycle, if you integrate between pi to 2 pi, okay, negative high cycle, you have again 2 times Vp. So in the end, you can derive that the equation to calculate the average voltage for the full wave rectifier. Okay, this is for full wave rectifier equals to, you can say call it V naught, for example, is 1 over 2 pi multiplied by the 2 Vp plus 2 Vp. Okay, because we have both have some value for both cycle. So in the end, if you simplify, you will have the average voltage is 0.636 multiplied by V peak or equal to 0.9 multiplied by VRMS. Okay, this is for full wave rectifier. Remember, for halfway rectifier, remember this value is 0.45, right? So 0.9. So basically 90%. So the average voltage for full rectifier is 90% of the VRMS. So it's more sensitive. So greater voltage is passed through the full rectifier. Okay. So, and then there's also some few formulas to calculate the peak value. Vp is VRMS multiplied by square root of 2. And to calculate the average value, V average, as I mentioned before, is 0.9 multiplied by VRMS. Okay, I will show you just now. And to calculate the AC sensitivity, okay, to calculate the AC sensitivity, you can use that the formula is SAC is 0.9 multiplied by SDC. Instead of, remember before, for full wave, it was 0.45, right? So now for full rectifier, the AC sensitivity is 0.9 multiplied by the DC sensitivity. So to calculate the DC sensitivity is the same as SDC is equal to the total resistance divided by the range voltage or 1 over the total current. We'll see some example after this. So to calculate the total resistance is VDC divided by IT or SAC, the sensitivity AC multiplied by the V range. Okay. So we go through some example to show how to use this one. Okay. So some few notes on full wave rectification. When we use a full wave rectification, the pointer will deflect to 90% of the full scale. Okay, what does it mean? So for sensitivity. So for example, if you have a 10 volt RMS, it's equivalent to 9 volt DC. Okay, because 0.9 multiplied by 10, right? So this means that AC voltmeter using full rectification has sensitivity equal to 90% of the sensitivity or twice the sensitivity of half rectification. So the multiplier resistor would be 90% of the value of the multiplier resistor for a 10 volt DC voltmeter. So the equation for computing the value of the multiplier resistor, okay, I just showed you now, is the multiplier resistor RS is VDC divided by IDC minus the internal resistor. Okay, so in the end, the SAC is equal to 0.9 SDC. Okay, so this is the two formula to calculate the multiplier resistor and the AC resistor. Okay, let's take a look at one example. Okay, this is a circuit. So you have a sinusoidal voltage here, AC voltage here, and the ERMS, so the RMS value is 10 volt. Okay, and you have a series multiplier resistor is 10 kilo ohm. Okay, and you have a full scale current diffraction of 1 milliamp and internal resistance of 100 ohm. So consider this that, for example, if you have a peak voltage, is quite multiplied by VRMS, so you have a peak voltage of 14.14. So the average value is, remember that V average equal to VDC is 0.636 multiplied by VP. So approximately around 9 volt. Okay. So you have 10 volt RMS and we have 9 volt of DC voltage. Okay. So therefore we can see that the 10 volt RMS voltage is equal to 9 volt DC for full scale deflection, which means that the pointer will deflect 90% of full scale. Right? This is just repetition of previous slides. So let's go for one example. So the question here, the circuit here is given. So this is a full wave rectifier. So this is 1, 2, 3, 4 diode here, and the RMS voltage is 10 volt, and you are given a 10 kilo ohm resistor, and the full scale is 1 milliamp.